I'll show you now how to perform nodal analysis on a circuit that contains voltage sources and current sources. So again, the first step is usually to identify the essential nodes. So I'll go ahead and identify them. I believe this is an essential node connecting 3 elements. This is another essential node connecting other 3 elements. And this one here at the bottom is an essential node that connects multiple elements too. It connects the source, the resistor, and so forth. And the next step after identifying how many essential nodes is, we know that the number of essential nodes is 3. That means I need to identify, well, at the end of the day, I'm going to identify one as a reference, and I'll be writing 2 equations to solve this particular circuit. But before I go and write these equations, I need to identify one of them to be the reference. And again, it doesn't matter. I mean, this could be the reference, this could be the reference, or this one. But typically, a good starting point is a reference point where a lot of elements are connected to. So this is here is a one of the reference nodes. Okay, and then we can go ahead and identify the other voltages or the nodes, or rename them so that we can write equations. So for example, we can write this one here to be my A and this one here to be my B. So pretty much I'm asking you to find VA and VB. And again, VA is the voltage difference between this point and the reference point, and VB is the voltage difference between here, this point, and this point in here, the reference point. All right, so let's go ahead and write KCL equations, because remember in nodal analysis, what we do is we write KCL equations at each one of the nodes. Typically, I showed you how to write these into currents leaving, but you don't have to really write them or redraw the circuit every single time you need to write the equations. You can go ahead and just write the equation right away. So I'm going to say, well, let's write KCL at point A or at node A. Well, here's the deal. So what I'm going to do is I'm going to focus on this current first. So this current here is going from the point A to point B. So it's VA minus VB and divided by 2. This is pretty much Ohm's law applied to this resistor, the 2 ohm resistor. What I did say, we know that Ohm's law tells me that the I is just simply V divided by R. Okay, what V? Well, the voltage drop across it, and since I'm assuming it's leaving, that means it's VA minus VB. Okay, divided by the R, which I know is 2 ohm. Okay, so KCL tells me, well, the other current in here, the one that maybe the one going down in here, and I know that the voltage drop across this 10 ohm is just simply VA. So this here is just simply VA divided by 10. And the last current is actually the one going in here, which I know that it's actually the opposite of the 2 amps. So I'll just say -2 equals 0. And that's the first nodal analysis equation. And as you can see, we're able to write the equation very quickly without actually having to identify, oh, the currents are leaving and whatnot. You do not have to write those. You do not have to do that. All you have to do is just figure out what the VA, or an equation that contains VA and VB. That's our ultimate goal. 2 equations, 2 unknowns. Figure out what the VA and what the VB is. I'll be able to figure out everything about the circuit. So I identified the first equation. We typically clean it up a little bit. We just say, well, this should be probably 6 divided by 10. I'm just doing this calculation in my head. 6 divided by 10 VA minus 1 divided by 2 VB. And that should be equal to 2. And that's basically the first equation. And I'll just highlight it in here and just say, well, this one here is equation 1. All right, we go ahead and just say, okay, similarly, KCL at node B. All right, so we're going to start. We can start with, you can start in any order you want. I started with the VA in here, but for the VB, I can start with the opposite current, which is here. So in this particular case, it's VB minus VA divided by 2. And again, this, because I'm assuming that the current is leaving this particular node, so it is opposite to the one that we wrote for this one here. So you will see in this particular case, we said VB minus VA divided by 2. Previously, we said VA minus VB divided by 2. Okay, we continue. The voltage or the current going through the 5 ohm is simply the VB divided by 5 based on Ohm's law. So that's here, VB divided by 5. And the last current is here. So the last current is the one that, and I'm going to highlight this here so that we can track it with me. I typically do not, but after, for the first time I will. So here I'm going to assume that this is some sort of a current, and what I'm interested in is the value of that current. So that current is going through this resistor, and I need to identify the voltage drop between here and here. Okay, so if I assume that this is positive, this is negative, what I'm effectively asking, I want VB minus, well, I know that this point in here is just simply 10 volts above the reference. So let me reiterate what I did. What I know is this is a node. This is not an essential node. It's just a node because it's only connected to 1 ohm and the 10 amp. But I also know that this node in here is the positive side of the voltage source, and the negative side is directly connected to the reference point. So I know that this point in here is 10 volts higher than the reference node. So I can just simply say, well, this one here is 10 volts. That's what I can say. So now what I'm interested in is the voltage across that 1 ohm. Well, it's simply VB minus that 10. So what you need to do is you need to tell me plus, that's VB minus 10 volts. Okay, and based on Ohm's law, because remember Ohm's law is V divided by R, I have to divide it by the value of this resistor, and that is just 1. Okay, and that equals 0, and that's the second KCL equation. Again, typically I do not identify these in pink. You should be able to see that pattern as you do more and more exercises. So we'll clean up this equation a little bit. So that's negative 1/2 VA plus, I believe that should be, it should be 7 divided by 10 VB plus VB actually. Let me just correct that because I forgot this VB here as well. So because I have 1/2, well, let me just write it down here. I think it's just simpler so that you can see it. It is just simply 1/2 plus 1 divided by 5 plus 1 VB equals, well, 10 divided by 1 is just 10 in here. So what I did is I just moved this one here. So for this half, it's this 1/2, 1/5, and 1. These are what you see in here. So we'll clean it up a little bit more. Okay. So that will become negative 1/2 VA plus, I believe that will be 17 divided by 10 VB, and that should be equals to 10. Okay. And that will be the second equation in here. So I can just highlight it and just say, well, this is the second equation. So now what I have is I have two equations in here and with two unknowns. One is VA, one is VB. All I have to do is just combine them, figure out what the VA and the VB, and nodal analysis is complete. So let me give you these numbers. These will be VA will be 10.91 volts and VB will be simply 9.09 volts. And so I have these two voltages. Let me just write them up in here. So this one here is VA, which is 10.91 volts, and the VB is 9.09 volts. Again, what I'm saying is this point is 10.91 volts above the reference, and this point in here is 9.09 above this particular reference in here. Okay, so if I want the current, for example, going through this resistor, all you have to do is just tell me, well, simply I is VB, okay, which is 9.09 minus VA, which is 10.91 divided by 2. That's basically the resistor, and you can compute that number, and that will be simply negative 0.91 amp. So of course it's in the negative because I assume that the current is going that way, but of course it's going the other way because I know that this voltage is higher than this voltage. I should have assumed it that way, but so be it. So we can just basically assume that this is negative 0.91. You can figure out all the other voltages and currents throughout the circuit, and you can compute the resistors and so forth. So for example, if you want this one in here, I recommend that you do that. Like for example, you can tell me, well, the current going in here is simply I is just VB, which is 9.09 minus the 10 volts. I did the same wrong assumption. That means the current's going that way because the voltage here is higher, but it doesn't matter. I made this assumption, so I stick with it, divided by 1. So it's simply also negative 0.91 amp. Surprisingly, it's the same numbers here. It has nothing to do with it, but it's just we got the same numbers